everyone, how are you all? I hope you are doing well. I am Dr. Nandita and I would like to welcome all of you to Aptdemy. So today I am here in this live session to solve a mathematical problem based on the law that you have learned on chemical kinetics. So before I start, let me tell you something. Online registration in Aptdemy is going on and you can register there and you can visit our website www.aptdemy.com. You can go there and register and there you will be able to have 24/7 access to all the courses that we are providing. We teachers are here to help you for all the face-to-face modes or problem solving sessions and doubt clearing sessions. So what are you waiting for? Get registered with Aptdemy. Now let's move on to the problem. So before I start the problem, I would like to tell you that several students have already requested me to solve this problem. But before I start the problem, let me talk about a little bit on chemical kinetics that we are observing in our day-to-day life. So you all have learned about the process of catalysis in the chapter chemical kinetics. So let me tell you a little bit about catalysis. What catalysis is? Catalysis is actually a process where a chemical species is involved in a chemical reaction and it actually enhances the rate of a chemical reaction. Right? So basically the function of catalysis is positive, that it actually enhances the rate of a chemical reaction and also it reduces the activation energy of a reaction. So you are always thinking about positive side of catalysis, but let me tell you a very common example of a negative catalysis. Where can we find it? We can find it or the negative catalysis influence for the ozone layer depletion. It's very common problem, environmental problem that we are facing nowadays, or we have come to know about this problem. So how it happens actually? So chlorofluorocarbon is a chemical species, right? So this chlorofluorocarbon is basically used in your refrigerators or in air conditioners basically because of the fact that they are non-corrosive, non-toxic as well as non-reactive. But due to this fact that they are non-reactive, they are actually used in air conditioners or in refrigerators, but because of the fact that they are not reacting with any chemical species to generate any new compound, what happens actually, they lingers in the Earth's environment and eventually they are drifting in higher altitudes and there they are actually getting deformed by the UV rays. So what happens actually, elemental chlorine is getting separated from the chlorofluorocarbon. Problem actually occurs when this elemental chlorine is encountered the ozone of the ozone layer, right? So what happens? Chloride ions are generated and the ozone of the ozone layer is getting transformed into the elemental oxygen. So the amount of ozone from the ozone layer is getting decreased time to time. So this is basically known as ozone layer depletion, which is actually a negative influence of catalysis. Let's take another very common example. When you are actually putting your food in refrigerator, you are actually applying the laws that you have learned in chemical kinetics. How? So basically what happens to your food when you are keeping your food in the room temperature? So what happens? The enzymes of the foods are actually reacting with the oxygen that present in the air and this causes to the deterioration or spoilage of your food very quickly. So basically in room temperature you can keep your food in a good condition for about 6 to 7 years, hours maximum, right? But if you keep the same food in the refrigerator, you can keep it for 2 to 3 days in a very good condition. So what is actually happening here? Here we can directly use the law of chemical kinetics which is known as the Arrhenius equation. So what we have learned in Arrhenius equation is that K, which is the, I'm sorry, maybe I have to go to the next slide for that. So in Arrhenius equation, what we have learned is that K is equal to A e to the power minus E A by RT, right? Here the K is the rate of your equation, A is the pre-exponential factor, EA is the activation energy of the reaction, R is our ideal gas constant, and T is the absolute temperature. And if you take ln in both sides of this equation, you will get ln K is equal to ln A minus EA by RT. Now if you plot K, that is rate of the equation, as a function of temperature, you will get a plot like this. And from this plot, you can easily say that with temperature, the rate of any reaction will increase, right? So basically what is happening, our room temperature is higher temperature. So the rate of spoilage of the food at room temperature is much, much higher. But as soon as you are putting your foods in refrigerator, what is happening? Temperature is getting decreased. So the rate of spoilage of the food is also getting decreased. So keeping your food in refrigerator is a direct example of Arrhenius equation that we are facing in our day-to-day life. And so this is based on the concept of Arrhenius equation that you have learned in the chapter of chemical kinetics. Now without much delaying, let's start the problem. So I am solving this problem based on many students' request. So let's get started. The problem appeared in Joint Entrance Advanced Examination 2022. The problem is match the rate expressions in list 1 for the decomposition of X with the corresponding profiles provided in list 2. X, S and K are constants having appropriate units. So from this you can check that in the list 1 we have some rate expressions. You can see, maybe I'll move it here. And in the right side, that is in list 2, we have some plots. And the plots are related to half-life as a function of initial concentration, and some of them in here we have concentration as a function of time in several forms. And several options are given. Now we will solve and we will check which option is fitting into this problem. Right? So let's start with the case 1. Right? So here you can see, I will write the rate expression again. So rate is given as K concentration of X divided by XS plus concentration of X. So this is the rate expression for the case 1. Now they are asking to solve it for all possible initial concentration of X. So we have 3 possibilities because we have to check for all possible initial concentrations, right? So the first case where our X concentration of X, if it is much greater than XS, what can we write? We can write XS plus concentration of X is approximately X. So our rate will then come out as K concentration of X divided by X. Now X will cancel out from top and bottom and we will end up with K only. And this rate expression is actually indicating for 1. Now another possibility is that if concentration of X is much less than XS. Then what will happen? We can write for this part that XS plus concentration of X will be equivalent to XS because XS is much higher than concentration of X. So what can we write in the rate expression? That rate would be equal to K concentration of X divided by XS. So we will write it as K prime concentration of X. I'm sorry, maybe I have to circle it. Yeah. So this part I will write as K prime. So this will give you K prime concentration of X. Now if you remember, this is nothing but the rate expression for your first order reaction. Right? Another case is also there, that the third possibility is that XS is equivalent to concentration of X. Then what can we write for the rate expression? Rate would be equal to K X divided by 2X because XS and X, concentration of X, are equivalent. So if you cancel out the X, we will end up with K divided by 2. So now if you check this one for zero order reaction, you can check for the least 2, you will be able to match these with P and S. So we will write that because you know that for zero order reactions, the half-life as a function of concentration plot will look like that, and the concentration of X as a function of time plot will look like that. So for zero order reaction, we can write this way: the case 1 will match with P and S, right? I will box it. Now, for the second one, because it is showing that it's a first order reaction, so we can write that for case 2, it is matching with Q and T, because half-life as a function of initial concentration of X will look like that for first order reaction, and ln X as a function of time plot will look like that for first order reaction. So which will match with Q and T. So case 2 is matching with Q and T. Now for the third one, the half-life plot, because rate is equal to K divided by 2, so the half-life plot must start with the origin of the plot. So this will actually equivalent to the plot which has been presented in R. So now, because the case 1 has been asked to solve for all possible initial concentrations, and we have solved for 3 different cases. So from the options, you can check that for only case 1, they are matching with all of the options because we are doing for all possible concentrations. So this is matching with P, Q, R, S and T. So up to this we have done for case 1. Now I will solve the rest of the problem in the next slide. Let's move on. But keep in mind that the case 1, for case 1 we have all the options that are matching, that is P, Q, R, S, T. So you remember this, I will use this information in the next page. Let's move on to the next slide for the same. Now we will solve for the case 2. So for case 2, they are asking to solve it for concentration of X are much less than X. So I will write again for case 2 the rate expression, that is K concentration of X divided by XS plus X prime, right? Now they have asked that initial concentration of X are much less than XS, that is X is much less than XS. So XS plus concentration of X prime can be written as XS. So rate will come out as then K concentration of X divided by XS. And this part will give you K prime concentration of X. This is again the expression for first order reaction, right? And as I have discussed in the previous slide, that for the first order reaction, case 2 will match with the plots presented in the list 2. Which are the plots? Q and T. Let's box it. Now let's move on to the third case, where they are asking that initial concentration of X are much higher than XS. So let's write the rate expression again. Kx rate is equal to Kx divided by Xs plus X prime. So because initial concentration of X is much higher than Xs, so for the rate, what can we write? We can write Kx divided by X. Now it is also giving you the rate expression for zero order reaction, right? So because it is zero order, so case 3 will match with the plots given in P and X. I have discussed in detail in the previous slide. Now for the final one, that is the case 4. For case 4, let's write the rate expression. Rate is equal to Kx square divided by Xs plus X prime, right? So what is the condition given? Initial concentration of X is much higher than Xs. So X is much higher than Xs. So what can we write for the rate is that Kx square divided by X, right? So this is again giving you Kx, which is again the rate expression of first order reaction, right? And as it is indicating first order reaction, so it will match with the plots provided in Q and T. So case 4 is giving you matching with plots Q and T. Now I will write down the matching one by one, and then we will have to decide which one is the correct option from the given options, right? So in the previous slide for case 1, we saw that it was matching with all the plots because we have done for all the possible concentrations. So P, Q, R, S and T was the matching. Now for 2, what we have observed, it is matching with Q and T, right? Case 3, it is matching with P and S, right? And case 4 matching with Q and T again. Right. Now from here, what can we write is that if we take for case 1 the P, for case 2 we can select Q, for case 3 as we have taken the P already, so we have to choose S, and for case 4 as we have taken Q already, so D is the option. So 1 is matching with P, 2 is matching with Q, 3 is matching with S, and 4 is matching with T. Now if you check the option, P, Q, S, T. So option A is the correct option for this problem. Now I hope I'm done with this problem. I hope you have enjoyed. And so what are you waiting for? Get connected and get registered with Aptdemy. We are here to help you. Thank you very much. All the best. Thank you. Have a good day. Bye bye. See you soon. Bye.